Good morning and welcome to the second lecture in statistical mechanics. In the last lecture, we were discussing the contact between statistics and thermodynamics. And we had considered two systems, A1 and A2, which were in equilibrium with macroscopic parameters N1, V1, E1 and N2, V2, E2 respectively. The system A1 was having number of microstates denoted by omega 1, which would be function of N1, V1, E1, and the system A2 was having total number of microstates omega 2, which was a function of N2, V2 and E2, and not the total number of particles, which is equal to N1 plus N2, E0 is total energy, E1 plus E2, and V0 is the total volume, V1 plus V2, where all these three quantities and not V0 and E0 were taken to be constants. When the systems A1 and A2 are allowed to interact, the total number of microstates available to the composite system is denoted by omega naught, and that will be equal to omega 1 into omega 2. As case 1, we had taken the condition that the energy exchange between the systems is allowed, but neither exchange of particles nor change in the volumes V1 and V2 is allowed. And we have seen that in such a case, the equilibrium will reach when beta 1 is equal to beta 2, where beta 1 or beta was dou by dou E of log of omega, which is a function of E, N and V, and this differentiation is taken at E equal to E bar, which is the equilibrium energy. So for beta 1, it is dou by dou E1 of log omega 1, E1, N1, V1 at E1 equal to E1 bar, and beta 2 was equal to dou by dou E2 of log omega 2, E2, V2, N2 at E2 equal to E2 bar. We have seen it in the last lecture. So when this quantity beta for the two systems are equal, we say the system has reached its equilibrium. Now, as energy exchange was being considered, and we know that when equilibrium is reached after an energy exchange, the two systems are said to be at the same temperature. So this beta must have something to do with the temperature that we will see later, and this equilibrium state is called the thermal state, thermal equilibrium rather. So the systems are in thermal equilibrium when beta 1 is equal to beta 2. That is the conclusion we draw from here. Now let's take the second case. We call it case 2. Let's take the second case. We call it case 2. And we allow the partition wall to move now. Means V1 and V2 will change. And this change in V1 and V2 will continue until an equilibrium is reached. So second case is when V1 and V2 are allowed to change, but neither N1 or N2 nor E1 or E2 may change. So that is the second case. We allow volumes to change, but we do not allow number of particles or energy to change. So, as we understand, for the composite system, the volume will keep on changing, V1 and V2 will keep on changing until equilibrium for the composite system is reached. So, suppose when equilibrium is reached, V1 becomes V1 bar and V2 becomes V2 bar. We understand that V1 plus V2, which was V0, will also be equal to V1 bar plus V2 bar, because total volume has to remain constant. Now, during this process of exchange, during this process of change in the volume, the total number of microstates available to the composite system will change. And now we can write omega naught, a function of volume V1 and V2, which is equal to omega naught, rather omega 1, a function of V1 into omega 2, a function of V2. We are taking omega as a function of V1 and V2 only because only volume will change in this case. But we understand that omega at any moment of time will be a function of all the three quantities N, V and E. So to maximize this omega naught, we use the same method that we have used when energy exchange was being considered in case 1. We may write omega naught as a function of total volume V0 and V1, because V2 will be V0 minus V1. So omega 1 is function of V1 and omega 2 now can be written as a function of V0 minus V1. So this equation becomes function of V1 only. So as V1 changes, omega naught will keep on changing, and when omega naught reaches maximum value, the change in V1 and hence change in V2 will also stop. So when we maximize omega naught, we write dou omega naught by dou V1 at V1 equal to V1 bar equal to dou omega 1 by dou V1 at V1 equal to V1 bar into omega 2, which is function of V2, but that omega 2 we will be taking at V2 bar, plus omega 1 at V1 bar into dou by dou V1 of omega 2, which is function of V2 at V1 equal to V1 bar. Using condition for maximum, this whole thing should be 0. So we write dou omega 1 V1 by dou V1 at V1 equal to V1 bar into omega 1, rather omega 2 at V2 bar plus omega 1 at V1 bar dou omega 2 V2 by dou V2 at V2 equal to V2 bar into dou V1, rather dou V2 by dou V1 equal to 0. From the condition V1 plus V2 equal to V0, which is a constant, we get dou V2 by dou V1 equal to minus 1, which when we substitute over here, we get dou omega 1 V1 by dou V1 at V1 equal to V1 bar into omega 2 at V2 bar minus, or let's write equal to, omega 1 at V1 bar dou omega 2 V2 by dou V2 at V2 equal to V2 bar. And we can rewrite this as 1 by omega 1 V1 at omega 1 at V1 bar into dou omega 1 V1 by dou V1 at V1 equal to V1 bar equal to 1 by omega 2 at V2 bar dou omega 2 V2 by dou V2 at V2 equal to V2 bar. So finally we get dou by dou V1 of log of omega 1 V1 at V1 equal to V1 bar equal to dou by dou V2 of log omega 2 V2 at V2 equal to V2 bar. And if we denote these quantities by say eta 1 and eta 2, we get the condition for equilibrium as eta 1 equal to eta 2, where eta is dou by dou V of log omega V at V equal to V bar, that is in the equilibrium condition. So when the partition wall is allowed to move, the composite system reaches equilibrium when eta 1 becomes equal to eta 2. Eta 1 is a quantity, say statistical quantity related to the system A1, and eta 2 is that corresponding to system A2. So when eta 1 becomes equal to eta 2, the composite system comes in equilibrium again. So unless eta 1 becomes equal to eta 2, the change in volume will continue to take place. Now this kind of equilibrium is called mechanical equilibrium. Mechanical equilibrium. So the systems reach in mechanical equilibrium when eta for the two systems are equal, where eta is dou by dou V of log omega at V equal to V bar. Similarly, we can take a third case where we will allow the particle exchange between the systems, and we will study what will be the condition for the system to reach equilibrium again. Now over here, we have allowed, if you take the second case, we have allowed the partition wall to shift. So this can move. So V1 and V2 will change. Along with this, if you make the wall conducting also, that means if you allow energy exchange as well as change in the volume, then for the system to reach equilibrium, both the conditions must be satisfied. Means beta 1 is equal to beta 2 and eta 1 is equal to eta 2. So if we allow the exchange of energy as well as we allow the change in the volume, the exchange of energy and change in the volume will continue until this condition is reached. Means both the conditions must be satisfied, beta 1 equal to beta 2 and eta 1 equal to eta 2. So one can understand that the two volumes will be in equilibrium when pressure on both sides become equal. That we know from thermodynamics. So we understand that this eta must have something to do with the pressure. Like we have seen, beta must be having something to do with the temperature, because that was thermal equilibrium. For mechanical equilibrium, the condition is eta 1 equal to eta 2, and for mechanical equilibrium, the pressure on both sides of the wall should be same. So eta must be related somehow to the thermodynamic pressure. So let's take third case now. So case 3. Particle exchange between the systems. Is allowed. Means N1 and N2 will change. But N1 plus N2 will always be the same. That condition is always there. So particle exchange between the system is allowed. No energy exchange or volume change is allowed. So these things are not allowed. Energy exchange is not allowed and volume change is also not allowed. So suppose when the equilibrium is reached, N1 bar is the number of particles in system A1 and N2 bar is the number of particles in system A2. So that means, as we have seen, N1 bar plus N2 bar must be equal to N1 plus N2, and that is equal to N0, which is a constant. So in this case, particle exchange will continue to take place until the equilibrium is reached. And we are taking that equilibrium is reached when number of particles in system A1 becomes N1 bar and number of particles in system A2 becomes N2 bar. That means now this dividing wall between system A1 and A2 is no more impervious. The particles can pass through that dividing wall. So as we have done in earlier two cases, omega naught now will be function of N1 and N2, which is equal to product of omega 1 N1 and omega 2 N2. So we can write as N1 plus N2 equal to N0. We can write this as omega naught N0 N1 equal to omega 1 n1 into omega 2 and not minus n1. So as n1 changes, omega naught will change, and this change in n1 will continue until omega naught reaches its maximum value. So if we maximize omega naught, we write dou omega naught by dou n1 at n1 equal to n1 bar equal to 0, and that will be dou omega 1 n1 by dou n1 at n1 equal to n1 bar multiplied by omega 2 at n2 bar plus omega 1 at n1 bar into dou omega 2 n2 by dou n1 at n1 equal to n1 bar. We rewrite this as 0 equal to dou omega 1 n1 by dou n1 n1 equal to n1 bar omega 2 at n2 bar plus omega 1 at n1 bar into dou omega 2 n2 by dou n2 at n2 equal to n2 bar into dou n2 by dou n1. But dou n2 by dou n1 is minus 1 because n1 plus n2 is a constant. Hence, we obtain dou omega 1 n1 by dou n1 at n1 equal to n1 bar omega 2 at n2 bar equal to omega 1 at n1 bar dou omega 2 n2 by dou n2 at n2 equal to n2 bar, which can be written as dou by dou n1 of log omega 1 n1 at n1 equal to n1 bar equal to dou by dou n2 of log omega 2 n2 at n2 equal to n2 bar. So particle exchange will continue to take place until this condition is reached. The left hand side we can write zeta 1 and right hand side is zeta 2, where zeta is dou by dou n of log omega n at n equal to n bar. So when zeta 1 becomes equal to zeta 2, the composite system reaches equilibrium. So the particle exchange will continue to take place until zeta 1 becomes equal to zeta 2, and then the system is said to be in equilibrium, and this kind of equilibrium is called particle equilibrium. Particle equilibrium or that is also called chemical equilibrium. From thermodynamics, we know that the particle exchange between two systems continues to take place until the chemical potential per particle chemical potential per particle of the system becomes equal. So the exchange of particle between two systems depends on the chemical potential per particle of individual system. The exchange of particles continues until the chemical potential per particle of both the systems become equal. Chemical potential per particle is the amount of energy required to make one particle move from one system to another system. When that energy becomes equal, then the systems are in chemical equilibrium. So we also understand that zeta must be related to somehow this chemical potential. So if we have to find the conditions or set of conditions for the two systems to be in thermal equilibrium, in mechanical equilibrium, and in particle equilibrium or chemical equilibrium, then all the three conditions must be satisfied. That means when beta 1 equal to beta 2 and eta 1 equal to eta 2 and zeta 1 equal to zeta 2, the two systems are in equilibrium. What kind of equilibrium? All the three. So the two systems are in thermal equilibrium, mechanical equilibrium, and chemical equilibrium if beta 1 equal to beta 2, eta 1 equal to eta 2, and zeta 1 equal to zeta 2. So we have found these results for the equilibrium of a system. Thermal equilibrium is when beta 1 equal to beta 2, where beta is defined as dou by dou E of log omega, function of E, at constant n, constant V, and at E equal to E bar. Mechanical equilibrium is when eta 1 equal to eta 2, where eta is defined as dou by dou V of log omega, a function of V, at constant n, constant E, and V equal to V bar. And chemical equilibrium is when zeta 1 is equal to zeta 2, where zeta is given by dou n of log omega as a function of n at constant V, constant E, and n equal to n bar. Let us discuss these results and find contact between thermodynamic quantities and beta, eta, and zeta, which are statistical quantities. We know from thermodynamics that dou E by dou S is equal to T, which is the thermal quantity, that is temperature, or we can write from here delta S by delta E is equal to 1 by T. Now if you take this condition for thermal equilibrium, from here we get beta equal to dou by dou E of log omega E at constant n, V, and at E equal to E bar. This relation is also at constant n and v. So, from these two relations, we can write, if you take beta equal to delta of log omega by delta E at constant n and v, we write delta S by delta log omega equal to 1 by T into 1 by beta. So that is equal to 1 by beta T. One can see that as we are talking about the system in equilibrium, this should be a constant. Now Boltzmann believed that the relation between this delta S, which is a thermodynamic quantity, and delta of log omega, which is a statistical quantity, must be fundamental in nature, and hence this constant must be a universal constant. This must be a universal constant because Boltzmann believed this relation between entropy and omega or log of omega to be of fundamental nature. So, now if you write delta S by delta log omega equal to a constant K, then we get S equal to K log omega, and this relation is called Boltzmann entropy relation. Boltzmann entropy relation. K is called Boltzmann's constant. Boltzmann's constant, and that is a universal constant. From these two relations, one can see that K equal to 1 by beta T, or beta is 1 by KT. We have earlier mentioned that as beta is related to thermal equilibrium, beta must have somehow a relation with temperature T, and beta comes out to be 1 by KT. You see, this Boltzmann entropy relation is a very important relation because for the first time Boltzmann showed a direct relation between the entropy S and the statistical quantity omega. And what is omega? Omega is the number of microstates corresponding to a macro state of the system. And as the system approaches equilibrium condition, it approaches a macro state corresponding to which the number of microstates is maximum, that we have discussed earlier. We know that when a system is left to itself, with passage of time it will approach the equilibrium state. Now, equilibrium state is that macro state in which number of microstates is maximum. So with time, a system will gradually pass through those macro states in which the number of microstates will be increasing, and ultimately when it reaches the macro state corresponding to which the number of microstates, which is omega, is maximum, it reaches the equilibrium. Now S is k log omega. So when the system is approaching equilibrium macro state, omega is continuously increasing. So then the entropy S will be continuously increasing. So whatever process is taking place, the entropy of the system will increase. And we know from thermodynamics, a statement is there which says irreversible or spontaneous processes can occur only in that direction for which the entropy of the universe or that of an isolated system increases. These processes cannot occur in the direction of decreasing entropy. So, S equal to k log omega is completely in line with that statement of thermodynamics. Further, when omega is 1, S is equal to 0. Now what does it mean? Omega equal to 1 means the system is in perfect ordered state. So if the system is in perfect ordered state, the entropy of the system is 0. This equation S equal to k log omega allows us to actually measure the entropy of a system. We will know what is the value of S provided we know what is the value of omega. So now to find the value of entropy of a system, what we need to find is that when the system is in equilibrium, what is the total number of microstates available to that system. We have shown that beta is 1 by kT. Let's find what relation do eta and zeta have with thermodynamic quantities. For the purpose, let's take the thermodynamic relation dE equal to T ds minus P dV plus mu dN, where P is the pressure, T is temperature, E is the energy, mu is chemical potential, per particle. So this is the well-known thermodynamic relation. We also have S equal to k log omega, which we call Boltzmann entropy relation. From this relation we have dou S by dou E equal to k dou log omega by dou E, and dou S by dou E at constant n and v will be k dou log omega by dou E at constant n and v. Now from this relation d equal to Tds minus P dV plus mu dN, dou S by dou E at constant n and v will be equal to 1 by T, because when n is constant, this dN will be 0, and when v is constant, this dV will be 0. So we get dou S by dou E equal to 1 by T. We also know that at constant n and v, dou log omega by dou E is equal to beta. So this is beta k. And from these two relations, we get beta k equal to 1 by T, or we get beta equal to 1 by kt. This we have already proved earlier. or this we have already shown rather earlier. Now let's take another relation. From S equal to k log omega, we obtain dou S by dou V at constant n and E will be equal to k dou by dou V of log omega at constant n and E. From this relation, dou S by dou V at constant n and E will be equal to, from this relation, as n is constant, dn will be 0 and E is constant, so dE will be 0. Hence we obtain for dou S by dou V at constant n and E equal to P by T. Now, this is also equal to k into eta, as dou by dou V of log omega at constant n and E we have seen was equal to eta. So from these two relations we get this equal to eta into k. So from here we obtain eta equal to P by kt. As we have already mentioned earlier, that eta must have a relation with pressure because it is defining the mechanical equilibrium. So it must be related to pressure, so that we find eta equal to P by kt. Let's take the third quantity, which is zeta. From this relation we can write again dou S by dou n at constant E and V equal to k dou by dou n of log omega at constant E and V. Now from this relation, dou S by dou n at constant n and V will be equal to, at constant E and V it should be, is equal to, you see, as E is constant, dE will be 0 and V is constant, so dV will be 0. Hence, for dou S by dou n at constant E and V, we obtain minus mu by T. But this quantity, dou by dou n of log omega at constant E and V, is taken as zeta. So this is k into zeta, and that will be equal to k into zeta. Thus we obtain from here that zeta comes out to be minus mu by kt. So this zeta, as expected, is related to the chemical potential per particle mu. So if you write them together, beta is 1 by kt, eta is P by kt, and zeta is minus mu by kt. From a physical point of view, these results are completely satisfactory because thermodynamically too, the conditions of equilibrium between two systems, A1 and A2, if the wall separating them is both conducting and movable, are indeed the same as the ones contained in above equations, namely T1 equal to T2 because beta 1 is equal to beta 2, and P1 is equal to P2 because eta 1 is equal to eta 2. Similarly, if the two systems can exchange particles as well as energy but have their volumes fixed, the conditions of equilibrium obtained thermodynamically are T1 equal to T2 and mu1 is equal to mu2. The first one because beta 1 has to be equal to beta 2 and mu1 equal to mu2 because zeta 1 is equal to zeta 2. And finally, if the exchange is such that all three macroscopic parameters become variable, then the conditions of equilibrium becomes T1 equal to T2 because beta 1 is equal to beta 2, P1 equal to P2 because eta 1 is equal to eta 2 and mu1 equal to mu2 because zeta 1 is equal to zeta 2 for chemical equilibrium. So what we find here is that the conclusions that are drawn from the statistical considerations and the conclusions that we draw from thermodynamic considerations are exactly the same. We'll further see the relation between or the contact between the thermodynamic quantities and the statistical quantities in the next lecture.